Did everyone get my notes?
Yes. Yeah, everyone, I think even your brother, except your Chen.
I forgot it was.
It's okay. So they can.
Yeah. I mean, yeah, I did send those with the hope that that would, like, you'd be like, okay, good, you don't have to give a talk now, but like, so, everyone ignored my cry for help, so.
Yeah.
Yeah, so I'll say a bit just about cycle spaces in general, and then it's going to turn into sort of a thing where like if the author meant this, then we go this way, and you know, something like that. Right? So X is going to be complex manifolds, eventually dimension 3, and for the instance. Okay, and this as a set, first of all. So I have some finite indexing set. And here, CI are the same images. Well, sorry, so it's going to be Z1, but it's always going to be Z1. Some more notation, so we did this last time, but so ZX beta will be such that this class beta, then so it's potentially confusing, but this can be cycles. Catching this is okay. Okay. Check this. So now we have, depending on your object, it's sort of a definition or it's maybe you can, yeah, let's say it's a definition. So S will be reduced, this is annoying, but it's important, complex analytic space for future reference. So it's going to look like that. Okay. And now we want to make sense of an analytic structure over here, so we need to specify when this is topological and then analytic structure. So I want to specify when some set theoretic map like this is analytic or continuous first and analytic. So, okay. So definition. This is and a point S0 is continuous, respectively analytic. If one continuous support, i.e. if so continuous not S0, i.e. if the support either is contained inside U, then exists some neighborhood with defects inside U for all x dash, which is a two, this is more technical. So for all y, so for all y locally closed analytic subspace, so that this is not intersect the boundary. And z less 0 intersect by multiplicity of state exists x dash with the same property. And then the induced map S, F dash, sorry, sim in Y is, if I don't have this, continuous, respectively analytic. Is that legible?
So for every y is subset of x.
Yes, for every Y.
The intersection of the boundaries.
Yeah, so what's
Because, it doesn't intersect the boundary of Y.
oh,
Sorry. And the intersection with, necessarily the interior of Y contains k points out of the multiplicity. Then there is an open subset of S such that every point in S has that same property, so that this k is fixed. And then there's this induced k intersection out of the multiplicity map here, which has some, specified analytic structure. You want this to be continuous or depending on whether it was continuous. And one is
the last one you say there exists and what?
S prime.
there exists an S prime.
It's transpose, I don't know what's
Sorry, I'm going to start writing more clearly now because since I don't have much content to talk about, I should at least do this. Okay, so there exists an S prime with the same property, so that it intersects, the nearby cycles also intersect with k points. And then you have the map that takes an intersection of the cycle with Y. And this map, okay. So something that sort of bothers me a little is that,
So
yeah.
Multiplicity so right. It's clear because we are not assuming any. I mean, Y could be sort of very singular at a point where it intersects the cycle. I mean, I would assume that the definition, I didn't read Barda's paper, so. So I would assume that the definition of multiplicity is you write local equations, you look at the Taylor expansion because you have analytic functions and you look, where the Taylor expansion.
Sorry, I misspoke. Y is locally closed analytic submanifold.
Oh, okay.
Yeah.
And then it makes, but otherwise,
No, otherwise, you have no sensible notion. Y could be completely Y.
Yeah. So Y is submanifold, okay.
Yeah.
And okay, so that answered my first question. But then the next one is what if Y is kind of a Taylor so that it's so ZS0 would be what? Be a curve or something? Or would be
ZS0 can be a curve, it was a cycle.
One second.
So ZS0 is a one cycle.
yeah, and then so what if I choose Y and which is not the correct dimension but still satisfy this property? What do you do with that?
Still, so you mean Y is not Y is not dimension 1, but it still intersects in.
Yeah.
I mean, my understanding is that this is still.
How could that,
It cannot be an open condition.
yeah, I mean, I kind of moved that a little bit then.
Yeah, it should.
Maybe there's some kind of a, I don't know. Not, well, kind of transversality. Some kind of transversality requirement saying Y is a complementary dimension that.
Yeah, let's just print that one. So then this intersection is transversal and it wants to multiplication into something like that. But yes, otherwise I agree with you. Okay, so what I was going to say is, so now it's a theorem that this thing exists as a reduced complex analytic space, or rather, I mean, this implicitly named a sheet, and it's a theorem that it's representable by a reduced space. So the grammar of that is that we can test it on reduced things, and it's representable in that category. So it's not like it's a complex analytic space with the property that it's reduced. It's an element of the category of reduced complex analytic spaces. So you can't test if that comes in here or something. So I don't really know how you compute deformations of cycles with that in mind. Like this, that was forced from there. So that's this. Yeah. Yes, so examples. This is projected space. And then if this for Earth inside P associated to this, some hypersurface is PQ across PQ. By C is the locus of I 0 by 1 such that C intersects 0 by 1 is not empty. So in this way, I think it's C as some line. It's line inside. Gamma will, well, D is 3. D, and then it's like this, and associate in the same projected space. And that describes it for projected space. And if this is polarized, then you have just here depending on I don't know how real this dependence is. This is a purely algebraic question about Charles Hughes or whatever, but I don't know how legitimate this.
Sorry, say it again.
I mean, if I choose
I was trying to parse the other definition.
right, yeah, if I some polarization of X, just not getting projected space, then I get some cycle thing in here. You know.
Yeah.
Well, I suppose since we already sort of sketched what function this is supposed to represent, but not really, we can say that it's independent, but don't want to be. Yeah, I don't want to make any sense about that. Now, in fact, is compact. Right? Yes, this would be seen from this or something. But in general, so this is not true, even if X is proper. So example, with Cx, well, beta equals 0 actually. So beta is always an element of H over Fx, non-compact. That's proper. Is H inside PC like disjoint smooth conic. I include along any abstract isomorphism of the line of the conic. I take the quotient fixed by this. Then homology class represented by the line is 0 in this quotient because it's equal to twice itself. And this is so actually the homology class of the line is in the same component as the homology class of the line where the lines. So the line ends up in the same class, sorry, the same component as the degree D curve for LD, and it turns out that this is not compact. This is Q, I guess, the quotient. Q of beta equals 0. It's 1. I think it's stuff like this that makes us need to work with complicated physical motion.
Degree, and then you have a line to a conic.
Yeah.
It's like E3. And so, okay, so then you say the curve with we won't generate any new curve or something.
No, I don't think we generate any new curves, and you kill the class of the line.
So what is, this is E of Q beta equals 0.
No, this is not compact.
So why is that non-compact?
Right, so I don't actually know exactly why it's not compact, but it feels plausible because, for example, let's take a degree D curve. Sort of generate lines. This will go to this is the generate L, and D times L is going to be in the same component as L for all D in this quotient. Because L is in the same component as 2L. Because there's a family interpolating the conic and the line, and now I push them to identify the right conic. So twice the line is in the same component as the line, you add them together, 3 times the line is in the same component as the line. It feels reasonable that this means it's not compact. Also, all of those will only trust those.
So basically what you were saying was it's beta, so all these are beta equals 0.
Yes.
If I take arbitrary line, not the line you're writing, then this line take a limit can go to your line, like
Yeah, it lies in the same component.
or conic, and then that becomes just the same as the line. So therefore, you have many of these copies. Things glued together. Many of this kind of a dual. I mean, I don't know whether it's it'll be almost still P. Line P.
Yeah, I mean, yeah, the point is, it's a kind of like class.
About this.
Yeah, you have some family. Elements, 2 elements, 3 elements, 4 elements. Just 2 elements to push forward of the conic, and elements to push forward of the line. Okay, what were it's the cost of 2 elements.
But
So in the same component class, in the same component.
doing any equivalence classes.
In the same component.
Is a geometric gluing, so I think the notation is a little bit misleading, that's why I was.
I don't know if it's right. It's not even sort of components of.
It's really a line, not just line, I mean, this.
Yeah.
L0,
Line, you fix a cardinal,
conic, and you have a,
then by some analytic isomorphism, so that thing becomes still a manifold.
it's so the way it's always.
Well, that's one of those things, yeah, just in schemes, I mean, it's, yeah.
You can glue, but it's a gluing still could be something smooth. Because the neighborhood are a little different, right?
Well, I mean, I think it's not just a set, right? So I think then, I think it's a localized morphism.
No, but I'm saying usually if you want to glue things, you also want to, you kind of doing like surgery, you want to kind of match not just that. Otherwise, your chart will be kind of very strange. Does that make sense? If you glue 2 things, you know, if it's a manifold, then you have a chart which kind of contains both the neighborhood. And then, but the neighborhood for Li is kind of you know, so it's O1 direct sum O1, right?
Yeah.
And for conics, it's different. It's different from O1, for example. So, I mean, you can certainly glue them, but it's the glue actually, it might not be smooth.
I think it should be smooth.
Is it? If it's smooth, then you should be able to tell me, like, you know, the local neighborhood of this. I mean, maybe it is, I mean, but what's the local neighborhood of, in this queue of this glue, like, you know, L, like let's call this line L0 and conic C0. What's
the normal one?
yeah, what's,
I mean, it should be 0, right? Like it should be sorry, O plus O.
but on, I could look at the line side, it's O1 plus O1, and look at the conic side, it's O plus. You know, it's kind of, it sort of
Yeah, the reason I was saying it should be O plus O is just because, you know, it should morally be the same thing as the fact that the push forward homology class becomes 0. Because it becomes identified with double this.
Yeah, but that's what made me wonder whether it's not smooth. I mean, so if their 10 classes are the same, then you can at least say it's kind of differentiably, you have a good chance of being differentiably isomorphic. Not algebraically, but differentiably, not homomorphic, but differentiably isomorphic. Because neighborhood is still, you know, if one of them is O, the rest of O2, the other one is O1, the rest of O1, then, you know, I don't know, steeple winning class are the same, something like that.
Yeah.
Topologically, they're the same. And you can glue them, but here, they're even topologically different. So.
One is O1 plus O1, and what's the other one?
Yeah, so conic is obviously now, I mean, the first chain class of line is 2, right? And
Yeah.
conic is 1, so they're different. So I'm a little bit worried where it's moving. Anyway, so even as singular, I think your argument is probably sound. You can still, and I can be convinced, even though I haven't convinced myself that this one doesn't have a new cycle. Cycle should are we creating cycle? That one cycle. The argument would be just like I maybe have lines in P3, and these lines in P3 originally formed some kind of dual base of this P3, and then become not dual, Quaternion, yeah, that's right. Not dual, but Quaternion, yeah, G2 4 of this. Then this is kind of a glue to another component, and another component glue to another component, etc. Something like that. So if infinite copies change degrees, then it's fine now a finite type. But I really think it might not be smooth. Not even topological.
I,
You see what I mean? So
I don't see how we can not be smooth topological. I mean,
yeah, just think about curve. If you have two curves glue at one point, it cannot be smooth, right?
no, I agree with that. I don't think this is an example of that, or even a good analogy. But stepping out of the video, because I don't like thinking on videos. give me a second.
So what's your argument? That is
Not relevant for this.
And
Because
yeah, I understand.
it's always the same, right?
No, I had convinced myself this was a local isomorphism, which I think purely topologically it is. In the there, because I can choose disjoint tubular neighborhoods of the line and the conic. I assume they don't intersect. I can choose disjoint line. So I had convinced myself because of that it was a local isomorphism. So I take a point here and a ball around it, and it's doesn't intersect. Where these then fine, whatever. It's just getting a bit.
Yeah, that part I'm perfectly okay. And
And then I take the line, they're not making any identifications on this ball.
then you have to worry about whether you do all these can be consistently done, right? So I mean, certainly, if you do it one neighborhood, you're okay. So imagine you have a sphere, like one sphere, right? Topological is two sphere. Now you have like different neighborhoods, and you are trying to do them together along your two sphere. And so, of course, locally, I can always do them. But I'm not sure globally can do them, because globally you have like R4 bundle over this. You also want to make sure after glue it, you also still have R4 bundle. Like even just like differentiable topology, you want to do that. And so certainly you can glue locally. I mean, because all bundles near a point on any point is trivial, so you can glue them. But this is exactly, can you identify these two, so we can kind of, I mean, if you cannot identify them, how can you glue them? If you can glue them, then you can identify them. So or at least they're kind of subjective map without kernel or something. I don't know. I mean, how you're going to glue them? Well, my example was bad. Yeah, so see. Yeah, I'm really worried. I mean, certainly if you step out of a smooth personality, I'm okay with that. But is this the example? So example which is used? And because
No, nothing, not anywhere. I wanted to give an example.
Oh, okay, so.
Yeah. So, yeah.
Yeah, I'm a little worried this, but it's still very good.
Where are we? Okay. So I am constrained to using these two boards because of the
Okay, sure.
Yeah.
Whatever. While you are at it, you might want to push.
the other one.
Yeah.
Okay, yeah, so more. So, you know, this we've seen before. This, so just, well, so a point B and a cycle of V, a cycle in the fiber over B. So this is like the only sort of sensible notion if you want it to be kind of a B local object. Because, you know, for example, and then B it's like that's exactly like this because you know, there's no curves in the base. So if you want it to be local, B is supposed to be this thing. For instance, okay, and comes with
Yeah, but that is only defined as a set, right? So the kind of a hardness, this non-definition is just defined as a set. And then you have to kind of give that some, you know, because after all, you at least need to give that kind of empty space.
okay, so X maps to X is continuous just a thing just from here, and it's probably like what's just the induced here. I think that should get it done. Probably this pins down. Remembering this probably pins down the topology, but since there is a map to this, I think maybe the cleanest way to present the analytic structure is by saying the composition is.
Yeah, but so when you no, but what does mean? What do we mean by X over B? Because there's no X. If X, let's say B is a curve, then X is n+1 dimension instead of n dimension, right?
Yes.
So I mean, and then so I think Harlan has kind of been abusing notation when you say X over B. And of course, when your B is really the whole simplex, that's always topologically trivial. Then you can always think about X as kind of at least trivial over B, up to isomorphism. But the B as defined to be any reduced L space.
Yep.
Then there's no map to X because that I don't know. I mean, which X are we talking about, right? So
I
we
don't
have a family of X.
X is the total space.
Yeah, but oh, you mean total space?
Yeah, X is the total space.
And so what do you mean pin that down?
I mean the choice of a point B in the base and a cycle in one fiber induces a cycle in the total space.
That's right.
So this map,
Yeah.
this is the definition of this, right? And that's all I mean. I'm not assuming anything about the base being. I'm not assuming any Ehresmann's theorem thing where I identify all the fibers topologically or something.
Okay.
Yeah, X is the total space.
What I was saying about Harvard's notation was you use the same X for any B. So, you change to like one simplex and two simplex, you still use the same X.
Yeah.
Okay, anyway, that's my main.
Yeah. So it is unfortunate.
And you say X is a complex threefold, and then you go ahead and say T of X over B.
Right. Yeah. I mean, it would be nicer if this was called pi. Pi this, and then I could just call pi a threefold. So this is what this is.
Okay.
And it gives cycle in a total space. And no assumptions on B right now. We are going to get to my conclusions about the simplices in a minute.
And do you think the Dio's definition works? Like, do you want to replace the Z?
I mean, I think not only does the Dio's definition work, but it might. One of the only things that works is it might work better than Parden's. Parden's thing I can't parse. I can't parse this thing is called a double complex. Right? I mean, bottom square looks this, right? Right, and then this is the total complex. What does that even mean? There's a map going in here and a map. It doesn't make sense. So Parden's theory, in my opinion, is ungrammatical in some substantial way. And I think we're supposed to understand those product signs as just kind of evocative of the limit being taken. It's literally not the thing he writes, which means as well, right? If it was an honest double complex, and okay, here, just any of the elements in here, let's specify a curvature relation theory, because it's like necessarily a cycle which is always zero. And curvature relation theories, in fact, are incredibly hard to find down. So it doesn't work. So I mean that's why either a Diels thing or a version of a Diels thing where the bases are all constrained to be simplices are at least grammatical. But Parden's thing ruined my weekend, so I'm quite like annoyed.
Yeah, I guess you have to. There is a double complex. You have to kind of do some kind of limit. You first do a truncation, then you take some limit, because then you work on the left lower corner instead of right lower corner. And then you should take some kind of limit.
I mean, there are various things you can do, but I think you should just take a limit right from the start. And not.
Yeah, well, I'm saying, you have this, and then you first do a truncation here, and, and then you take double complex from the lower left corner instead from right corner, as you pointed out, it doesn't work. Then you take some kind of limit.
Yeah. It's other things right. Yeah, I mean, you should do it just one element. You shouldn't do this as like for a fixed X or for a fixed family X. You should just do this as one element, which is some C round infinity or C compact. And then you should be taking a limit over diagrams with these things, like in the infinity. I mean, 180, that doesn't. Anyway, so one more sketch definition before we come to the bit that is not being referred to. So semi-charts. So some cycle like this. So the disrupt unit for normalizations. But the normalization is mapped through the curves, and I can think of this somehow as compared to X. We look at all definitions of the so these are definitions. Yes, so that's units computed by. Imagine it's connected. It's computed by this. Just like any definition problem, So we're allowed to perform these things individually, the map. And now we look at the locus of all of these things, which is not quite precise, but I'm going to kind of accept it. The locus of all sub missions Z, which contains Z, is by definition, again, by definition, the semi-char. The semi-char is the end, it just means, well, it speaks this. So the word semi-char does not, it will, like, it doesn't tool to some pre-existing definition of something, it's just a word.
So in other words, I would like, in the neighborhood of this kind of, I don't know what's the right name. I mean, in neighborhood of this map, I will be missing a lot of other things.
You could be missing things. So it turns out generically you'll get something open. So this is not a lemma. So the set of Z, so Z is a cycle, so that SZ is open. So then we're into this stuff. Is dense.
Yeah, I can agree. So because you see what's the difference between this deformation and maybe embedded. So I first consider this as a map, and then I will separate this, right? So then I don't, so I would be thinking about this some kind of accidental image. I have like, let's say I have a crossing in the image, and I always would do a two-wise, and I will separate them. Right?
Yeah.
So, or if I don't know, the domain curve, he might have some kind of restriction. I don't know, maybe. Anyway, so what would happen? So when I deform, I can just freely deform these two because they might be just actually disconnected, or at least they're. So let's say that it's connected, so I can freely deform them. While, and this generically won't hit. What would it hit? All the embedded deformation.
So I'll do an example maybe. Just some examples. Once again, constraints. I can make this smaller first. So and then so yeah, it's like a clinic, two lines, 30 lines, and double. Yeah. Okay, so here the semi-chart is open. Here it's open. Here it's not. Oops. Yeah, so for example, just the see this one is open. Just looking at deformations of this map. And I can deform these only trivially, and the map G3 only deforms in the normal direction, so I only ever get lines, I never get the clinic nearby, but there are clinics arbitrarily nearby. And in particular, like I said, there are clinics arbitrarily nearby, so at least the lemma is plausible.
Yeah, and let's say,
I'm inclined to agree with the lemma as well.
okay.
I couldn't understand the proof, so I'm not going to give it, but the lemma is very reasonable.
Yeah, I agree. I was actually going, I was saying.
That's exactly example. Yeah,
Exactly what.
yeah.
Right.
Yeah, so now get to the sort of universal stuff. It's notation between sets. Yeah, and if C is a category, dash simplify like this. And probably won't use this sequence semi-simplicial sets.
Sorry, when you say was C lower triangle,
Yeah, simplicial objects. Simplicial, yeah.
so what does it mean? You mean like like it is like delta up all the function
Yeah,
delta
yeah.
to C?
Yeah, so function the opposite of the category of time orderless to C.
And so what is your injective?
So only.
Oh, okay, so you're only considering the
Yeah. So also,
and strictly, is that strictly increasing? Yeah, strictly increasing.
well, injective force is strictly increasing. Yes. So yes, it's strictly increasing, and it means
The same as the injective, right? So
yeah. Exactly. And yeah, so the relevance is then the simplicial set. Yeah, so simplicial sets like
yeah,
yeah, so here's delta one cross delta one, and this is two simplices in the delta one image, whereas this is technically a two simplex as well, right? Since it's not at first degeneracy not two simplices. And then this fact here is telling me that this is good enough to know the geometric realization. Like you only need to know the simplices of the maximum dimension, which corresponds to the injective things, and so setting simplicial sets are good enough for taking geometric realizations and whatever. Right, so definition of the whole word.
in other words, so basically, so I'm sorry, so I'm not
Yeah.
aware of the video set. This image video set, it's just basically in the subcategory of this category, so that you just remove the degeneracy. So you only allow this, and therefore you don't have a degeneracy.
You don't have degeneracy.
Boundary map, but you don't have
You
degeneracy.
don't have boundary, you still have degeneracies, and it's a general fact that homological type constructions that you want to do, they factor through semi-simplicial sets. So, for example, in the Dildcan correspondence, you can normalize by pushing things out by the image of degeneracies and so on. Like, in fact, you asked a question about this before when I was doing a Hochschild homology talk, and I wanted to ignore all the ones, which was an example of taking a normalized yeah, so, okay. This to me is a complex engine, right? Which means locus n plus one couples the sum to zero and one. To one, yeah, I meant to say to one actually. Yes, and this defense is something object C, okay, and now there's a weird thing. which is that Hardin doesn't seem to want to work with this. I don't really understand why not.
Yeah, exactly. So I thought, when I asked people and they said that's the simplicial kind of a set. So
I mean,
Bouaziz was using, why didn't he use this?
yeah, it's not just about
The real part of this.
So I don't really understand why he wants like some sort of compact skeleton that he's keeping around. I don't. So his definition. So first, so I can more accurately complain about his definition of I should state it.
So this delta and C is topologically homotopy to delta n R. Is that right?
Yeah. I mean, yeah, what's contractible? What's contractible? So.
Oh yes.
So his yeah. So his definition of family, his definition, Hardin writes a family, and you should think of this as a R. F, I is my name for families, is a pair. So that's and R is neighborhoods. C and X goes to D. Right, that's the definition, and the quotient is by refinement. So like if you that here, then I identify the family over you and the family over that. Okay, so implicitly he's defined some other object, which is like
Yeah, I remember correctly. He didn't even use delta and C. He just said C N or something.
CN plus one. It's fine. It's well, I think it's well, it's be over here. But yeah. So okay, and this is going to be this. I mean, which is so it's for you sandwiched in here. All off from this by definition is the value of the frequency. Right, so this is reissue name. And just this delta set on whatever. This is essentially a definition of a function. And it's a co-limit because you're taking, that's the relation is that you identify things for the agree on germs, so germs are always a co-limit like that. Another very interesting point, which is that n goes to not log n is slightly differential. Well, this is sheet really. So I'm basically just going to ignore this point of the work over this, because in particular, an family over U does give me 1 over delta NC. And at first I was confused about whether we consider the empty set to be a 3-month full node, but later on he does. So this counts as a family of 3-month nodes, because the extra fibers that are empty, we agree that they're 3-folds. So forgetting that nonsense about the empty set, the point is that I'm just going to be working with this. Not his.
I'm just like,
How can that be a what?
I mean, he's basically saying that's kind of equivalence class.
Yeah.
A family over kind of a small complex form.
Yes, so this,
Now the real n-dimensional simplex. And we say equivalence condition if more than if they're restricted to this like real n-dimensional simplex is the same, then they're considered equivalent. That's kind of what limit is.
yeah.
So it has to be complex analytic in some neighborhood, and if they're in certain neighborhood they're the same, then they're considered equivalent.
Exactly. Yeah. And this is the definition of a family over this thing, which a priori doesn't make sense because it's power complex.
Yeah, so you,
No, but what I was asking is about the assertion that you can extend the family by.
No, there's no such assertion. I mean, there's natural maps indexed by when one goes into the other, and you're taking the columns over that.
no, you were saying
Oh,
you can, that, so, oh,
The family over U can be thought of as a family over delta and C.
why can't I just, so it maps to you and then it controls with the delta and Z. Why can't I do that?
I mean, you can, it's just not a.
kind of real family in terms of like, flat family or something. I mean,
Yeah, I agree, it's not what I would call a family threefold. So later on, when we discuss co-unitality of this co-product, we will convene that the empty set is a threefold, so it's, yeah.
I understand that the empty set.
Yeah.
no, and we said it's better, as a.
You mean the,
Not as a control, but what you're saying is
yeah,
really.
the Pythons.
Yeah, I'm talking about, like analytics
Yeah.
structure, not. That's fine. I mean, if that's not used, then
Yeah.
it's not.
Yeah, but I'm still kind of not convinced that's what you were trying to do. I think he gave a non-definition of what his family is, and I think he really did mean the flat family because he said like with three-dimensional fibers or things like that. So
I think it really means more than flat family.
yeah, it means smooth side. Yeah, of course. So, but usually I think he actually mean the family in the sense we understood. So
Yeah.
meaning it at least be flat. In this case, of course, smooth.
Yeah.
So
Okay, so
you should extend that, but whether that is, whether that maybe it's not all like you maybe not maybe there are always tension to delta and C, I think. So if you
you just like this scale up. So.
yeah, so what I have to write down what delta are to kind of understand that. But if you let's just say if n is equal to 1, right?
Yep.
And you have let's say what is delta n c, which is just a complex line, and I think it's kind of a complex isomorphic complex line containing the segment. So as long as you you have a neighborhood of the segment, like a ball, then you can more or less extend this to the entire family by kind of a dilation to the whole C, right? So at least
I don't see how you can do it to the whole C. I just see how you to do it to a fixed bigger ball. All I can see is how you can make it fixed. Yes, I mean.
yeah, but you can just basically make it bigger and bigger.
Yeah, but then, I mean, what's the limiting process like? Yeah. I just see how you can make a finite one bigger.
Or you can do the other way. So you can take the C and U. That's kind of a, yeah, so take some kind of a complex and map from C to open.
From C to what?
C to hard open disk and pull back.
There's no such by the OPO, right?
You get a different thing if you. If you take just families over delta and C and you require them to agree in some. neighborhood.
Well, I mean, they agree in some,
Fields.
they agree in some neighborhood just if they're the same family.
Sorry?
They agree in some neighborhood just if they're identical.
But that would be just going back. I was hoping that we don't have to ever invoke delta NR and then just use delta NC, like you said. And then hopefully that will give us the same thing, or maybe as Bill said, we shouldn't even bother.
Yeah, so I don't know if these two notions are the same notion. I also don't know where
He uses.
he uses some specific difference between the two.
Okay.
So that's what I meant about like being a bit worried that this sort of choose your own adventure thing was gonna happen.
Anyway, so okay, so let's just
So yeah, let's
that word
forge on.
and going ahead and yeah. So now we have to kind of remember like a master chess player. We always remember like backtrack. Somebody move, I put it down, and then each time I choose this, it's like 5 possible moves times 8 possible moves times 2 possible moves.
Sorry, so now what's your notation there? Outline things.
So now and not like you could call it delta and R if you wanted, but then you have to understand that delta and R is some feature on this type of analytic spaces. So by definition, nabla and it's a feature on so that X not to nabla and equals Arden's definition of a C-fold over the real space. Right, so by definition, some limit of open neighborhoods.
Did he say? Did he?
No, but I mean, implicitly it is, right? It's just so that I don't have to use his notation. But it's chief, like it's clearly a local condition. Right, and now as n varies, there's, I think, there's maps between these things, but I think it's always semi-simple because I think given such a thing, I think you need to use the fact that the face maps are open, but the declaration maps are not open. So only the face maps, you're unable, this thing only has functoriality face maps, which are the open maps. And this is kind of forced because this thing has functoriality for both, but it will only pass through an open neighborhood if you take a face map. That's why it's a semi-special thing, I think.
So you don't think he would actually, in fact, he wouldn't be able to use the.
I mean, I searched the paper for the word semi-simplicial and they show up. So it presumably has some relevance that he's aware of. And anyway, most of the giant universal thing that I don't think quite makes sense is the geometric realization and semi-simplicial objects are good enough for them.
Yeah, but he did say that he wanted this to be a simplicial group, right?
Right. Then unless I'm missing something, I'm not sure I fully believe it. I mean, I would prefer not to try to work it out on the board, but I guess we could is the right. So what's the point? So I wrote in my notes. I think something about this. So I think the thing he defines is still a simplicial group point, because you can still define pullbacks along both the face and the degeneracy maps, even though this thing is not a simplicial object. He doesn't make a claim about this being a simplicial object, I think. He makes a claim about what he calls complex 3 being a simplicial object. And then all you need is that for a map is n f and x times delta for now, and there's still a pullback. Okay, I'm going to write this off.
Yeah, so what you're saying is you cannot do the pullback map, like, from delta n, like
No.
delta n minus one.
Nabla and Nabla n plus one. So the Nabla n to Nabla n minus one should be fine because it's. It's open up.
Yeah.
Yeah.
So I'm saying pullback map.
Well, yeah. So, yeah, for a fixed family, I think it's fine in both cases. Yeah, so in my notes, this is a numbers confusion.
If, if it's okay, then why can you have degeneracy?
Why can?
Yeah, why you not? Okay, not.
In this case.
Yeah.
I think you can have the degeneracy maps because they're not going to extend to an open neighborhood, which they could have to for it to be. Oh, sorry. Okay, yeah, yeah, I think so. I'm not sure. I don't want to make any pronouncements on that, but I convinced myself that you don't have the degeneracy maps for this thing, even if it's the pullbacks and fellows.
It's the Jersey map basically saying if I have a like family over delta n minus one, I wouldn't think about this as a family over delta n, right? Then I basically just try to get the delta n kind of project to delta n minus one. The Jersey map. And I forward back. Can I do that?
I just write it for a second for myself. Okay, I'm not sure. I'm going to continue.
Yeah, one day.
Yeah. So just some notation. So this is a map of syntheses. And yeah, like this is the word n. Yeah. And the pullback is pullback family. So denote it like this. This. This is x plus. Right, and same for Nabla, because I think that's fine. That's a Nabla. Yeah, and so observation. There's an equivalence like this. This is more or less real. Right, and so this family is pullback, and this family, like it's not. So in particular, there's some isomorphism. And now so already this is
So by C red, is that called?
sorry, okay. So notation. So C round infinity is, as far as I can tell, what part of has decided to call around homology. And just because around more y is locally combined Hausdorff, combination with B Hausdorff is relative homology with the 1 point of infinity and 1 point of multiplication. So it's each of this real infinity. So that's the first piece of notation. So I'll remind you that real infinity y is y which y of the constant sheaf and e round infinity of y over x. So implicitly there's a map of y to x. It is y forward, and then the structure map is f upper t. So this is a realm where this is just what this means. A realm where, and this means relative for this family. Because remember, the cycle space over delta m is a family over delta m. Right. Now the existence of this pullback is because relative Borel number homology has pullbacks, which regular Borel number homology doesn't really have pullbacks. But relative Borel number has pullbacks for fiber squares.
What do you mean by relative?
Relative, so it's relative, that's nothing to do with the relative. Relative is y over x. This is the map to f. Y is the family over x, not family. Y is just a map to x. Y has a map to x. And the relative homology for, with respect to this map is defined by this. By this, just an exact analogy with the case of x equals a point. Actually, exact analogy would be to take x lower start here, and then the relative homology would be valued as the slot the base. But we don't do that. We take the absolute forward and the relative should come back.
And then when you write I y, you mean y mapping to a point.
So point. Yeah. Yes, so cohomology is coefficients in dualizing complex.
So you're distinguishing between you read relative infinity and what's then the other one is C red.
No, sorry, so that's also supposed to say round infinity. Yeah.
So there are two relatives there. One is on.
With respect to the fiber-wise 1 point complexification and one.
Yeah.
So if you replace rel infinity by
Bn, like a normal,
then the confusion,
like a normal person. Yeah.
yeah, and then you can write CBM rel.
Yeah, I mean, really what I want to do is have just be allowed to put a map and keep.
Yeah.
But that's what I prefer as notation, but I'm using the notation from the paper. Yeah, so I mean, to me, it's appropriate to pick a map and space out vector space. Okay, this is the map. Okay, and now so CBN of y over x, there is a pullback map. CBN. Whenever it's a fiber square. Yeah, it's provides. So relative version is getting more functoriality. Like the absolute version is just functorial for proper pushable control. And then you always get an extra base change to the thing. As a, yeah, I don't want to construct this some diagram face with the objects. The only input is proper base change to this diagram. So base change order street. Right, and then this observation gives you this map. Because this is actually a pullback challenge. So already this is diverged from what is going to happen in what happens in the paper, where he seems to work with absolute Borel-Moore homology, and then I don't understand what limit is being taken.
I mean, from your notation, absolute is actually more difficult, right? Relative is actually easier. This one's relative because you actually, it's all fiber square, and absolute actually not. I mean, it's not fiber square.
Yeah.
Work everything relative point, that's kind of harder in that sense. Like to get it from relative.
Yeah, the functoriality would just be when the map on total spaces is proper, then you have covariant functoriality, or open, and you have conjugate. Yeah. Right. My instinct was that, at least my intuition for what a curve enumeration theory or whatever would be, it should be like the when that specify the fundamental class on something over, say, a 3-dimensional simplex, that implies a compatibility on this. So curve enumeration theory is in Hardin's mind or something. It's like a specification of fundamental class, relative fundamental class, vertical fundamental class for each family compatibly. And I would have thought the compatibility condition would be I have X mapping to some, say, 3-dimensional base, let's call it, say, it's delta 3. And then I have a fiber over a face, so a face fiber, a face change. And then I would have thought the virtual fundamental class on the big thing should specify it on the small thing. Right? And so these things are living in relative Borel-Moore homology. So this is why I think the correct inferiority should be this. Otherwise, the only inferiority we have to the absolute things is from the sub over from the sub face family from the family over the face, you'd be able to push forward because it's closed, but that doesn't feel like the correct compatibility. It doesn't feel like the thing on the face should determine it over the whole simplex. It feels like the thing over the whole simplex should determine it over a face.
Yes. Yeah.
Right. So this is why I want this functoriality, which is not what's done in the paper, which is again.
But I mean, in the paper, the arrows go the fucking wrong way.
Yeah.
But when you find
Exactly. So
homology of that double complex.
Yeah. So I was hoping that I was hoping that somehow all the mistakes would cancel out or something. So far, it's getting worse. It's this thing is happening more than they're all kind of annihilating,
Right.
Yeah. Yes.
Okay, great. Thank you very much. I think we're starting to understand.
Okay, so I'll leave that up to taking on the functor implied there. So now we're just kind of recapitulating what the old sketch as a definition last time, except restricting the basis to these simple sets, so it looks vaguely like Hardin's paper. So definition of complex 3. So slightly different than in the paper. This is a category of objects. I could use delta, you could also use nabla, X, and family. And I'm going to use this for this. And you understand that there is an N and there is an X, so whatever. And morphisms are defined on objects. Morphisms defined to be a pair of morphisms X and Y, and that was sufficient sets. To an amount of finite sets, which in particular negative amount of sufficient sets, so that X maps to what is X map? X map to Y from here, that's an N from here, that's Y across N, so N is an X represent. So maps are pairs, so a map from X to Y, a map of sufficient sets, but witnesses X has a fullback of the family. So this is just constructed so that we actually have functor out by taking relative Borel or James. Okay, so there's a functor.
This is x. Why do you want to write x? Oh, okay, so n is the morphism.
Oh, sorry. This is a couple x, choice of n, and morphism like this. This haven't done it. I mean, I'm going to read into this conventional being pedantic. But the data, yes, if you want, this specifies all the data an x, an n, and delta, and then these are the ones. So Holmes sort of explicitly witnessed x as the pullback of the family. The x family is the pullback of the y family.
So that has to be isomorphic, right?
Yeah. So I want to say that x is the. Because I want this functoriality, so I wanted to. Right? Otherwise, I would get extra function. I could also say x is open in this or something, and then I'd be able to take a pullback as well. But I don't.
So that becomes.
Okay, so this is complexity. So lemma is not really a lemma. So there exists a parameter. So let's see all into dz, which does this.
So what is dz?
There's I just did the right category of the billion groups.
So and what is that? That's squiggly, like I don't know, squiggly z.
Cycles.
No, the
Oh, that's the integers.
Sorry, this is
okay, same
Whole category of three modules.
yeah. It's just thought this is hard if you want. Yeah, you just thought hard. And then you would have stuff this stuff. Just not just the part. So the target is this, right? So why is this not defined? It's not defined because it's the observation up there that it's not defined because it's the observation up there that fullback works well with cycles, and Borel homology has these base change morphisms, and from the fact that the morphisms in the category are grouped out so that this becomes possible. She can defunct her name. So this is what I want to work with. The thing I define right after this is what I want to work with instead of this double complex thing which doesn't exist.
yeah. So this will be something like dual to this cumulative.
No.
Actually, it's
No, he already writes down, so he's got the thing that doesn't make sense, and it's dual, which also doesn't make sense. So this will be something that replaces one half of it, and this will also have a dual version, which replaces the other half.
okay. So is this the replacement of the dual or the grothic group of one cycle itself?
So this is the one that curve enumeration theories live in. As I recall, the Grothendieck group is the dual of curve enumeration theories. This is the curve enumeration theory side of things, which is okay. So now
This is the dual of the grothic group of one cycle.
yeah. So this is where the virtual fundamental processes so can evaluate the dual thing in this. Right. So yeah, sorry, now I'm really then whenever you check this paper, you can tell which one it is because he uses relevant. Yeah. Okay. And now, so the first thing is about this does not correspond to the thing you wrote. But, this does. so this is going to be C relative infinity, then for the use. So this is the Curving inversion in his position. Curving inversion is the element of what's up with this class. And what's everything else against this? That's now it's gets over complex. Really not it's involved, I suppose. G where G takes not relative infinity but compactly supported analogy. Equals C size and this is the this is currently group and this is carbon inversion. So this
We haven't defined G yet.
so yeah, so
Anyway, so yeah.
yeah, G takes G is just like opposite to F, like take a dual object, we just come back with homology, not for homology, it's also a relative version thereof. Functoriality is the exact opposite functoriality when it's like a equivalent. So it's kind of dual in the most like sensible way. It's not like the dual of the limit or anything. I mean, the limit clearly doesn't have a dual in T to Z. Like in the sense that it's not generalized. So
This limit will be, let's see, so the limit will be respect to what? So your index set will be some kind of delta n?
no, so the index set is the category complex 3. So the index set is morphisms like this.
Oh, okay.
Okay. Okay, I'm going to keep talking about this, maybe so that it becomes more clear what this encodes.
Yeah.
Maybe so it's more readable.
Okay. The index set is actually the entire, so the candle.
Yeah.
CEF3.
Yeah. If you try something of that this size, if you grant that his double complex thing is roughly the correct size, then recall that there's terms like this, right? Which is really weird. I mean, these things aren't talking to each other in any meaningful way. Like,
Exactly.
yeah. Okay. Okay, so I want to propose that this is the better thing to consider. You could also, it's in the notes that I wrote, you'll see that there's also a version where I put a bold here, and that's just the version that's almost identical except by all on general basis, not just delta n. I think they should not be too different in this for the process. So what does so C round infinity it's defined as some giant limit, which means it has this mass evaluates that fixed family. Right? There's the mass of the limit. So this is the map eval like this. So it's a limit of a certain functor, so in particular it universally maps to the functor as applied to each object of the category. Right, and then again, by definition, a limit, the evaluations are impossible.
This is, I mean, as if you would have a universal family over this complex three thing, which is not a like space or like in a base of a space.
Yeah, yeah.
A base of a family.
Mm-hmm.
And then you would have, and this has various sort of maps.
Yeah,
Various clients to it, then you pull back the family and you're just saying that you're taking like you pull back this universal family, right?
And then take relative cycles of the universal family, yeah. And then in this case, so what these things being evaluations would be like restricting to a point in that space, because the point would classify.
Yeah.
But it's, sort of meaningless, but also, in your head, it's kind of maybe how you think of it. I think this is, there's a certain point that we call the carbon enumeration theory, compatible association of whatever to every whatever, and this is literally what this is, much more so than what he writes. So in particular, an element. So it's really hard to write down any elements of this, just because it's a lot of people's careers, working with one or two elements of it is very hard to specify. So in some sense, it tells you that it can't come from some honest double complex. Because then you just pick a vertex in the right corner and it would give you one, and but they're hard to come by objects.
Yeah, I mean, I'm sort of always, when I kind of scanning through this, I always thought this CPX3 is some kind of a infinite union of EN stacks which classify the complex threefolds. Then this Z over that, it's just like a fiber-wise one cycle. Like you have a universal family, and then you have, think about this, and then of course that stack might not exist even as Argand stack or something, but there I'm thinking about that, and so this evaluation is like, okay, so now if I have this classifying stack, then you just, this evaluation just taking this delta n and basically mapping that to just choose a morphism.
It's almost like we're shifting to a point.
So what we're really saying is that sort of even though the classifying stack and the universal family don't exist, the homology of such non-existent thing does exist, and it has the more homology.
Yeah.
What's that?
It's sometimes sheaves on some general diagram category make perfect sense.
Yeah.
Even when the limit or whatever of the diagram is just an absolute garbage object, there's nothing classifying it.
Right.
The actual limit or co-limit of the diagram of sheaves is perfectly sensible. And this is somehow an example of this. Right. And so okay, so dually there's one operation. This time goes that to me. It's co-evaluation maps. I guess we call them insertion maps or something. I mean, nothing wrong with in the sense, in that so this is just, sorry. So this is exactly dual. In particular, it's easy to write that element of the group. I think that element of this, which is very hard, because it's a limit, it's a limit, so it means Um, Is this like clear enough?
Do you have any sense of why it's calling it a Grothendieck group?
So I think so. If you first accept that this is part of the enumeration theory,
Yeah.
then the Grothendieck group is the so okay. This is carbon enumeration theories of with values in K or something.
Right.
You can talk about carbon enumeration theories with values in something else. And then the Grothendieck group is the universal recipient of a carbon enumeration theory, which like classifies the identity morphism on this.
I'm lost. Can you slow down what you said? I mean,
Yeah.
so I was thinking about Grothendieck group. I don't know why it's called Grothendieck group. In what sense? I mean, Grothendieck has many Grothendieck groups.
So I think the one you
So the one I was thinking about is like this Grothendieck group of
yeah.
Is that close to that?
I think so what's the point of the Grothendieck group of varieties? It's like
It sort of has this.
the universal Euler characteristic, right? Yeah. What is it for? An Euler characteristic is some pair chi in a ring so that it's multiplicative and whatever. And then well, the Grothendieck group is this topological thing valued in this. So what should be the case? Then it should be if this is a curve enumeration. Sorry, if this is the Grothendieck group, then there should be a universal curve enumeration theory value in the Grothendieck group. Yeah. Okay. So gradually this is curve enumeration theories. And then I think so. This is okay. Then you also have like K values curve enumeration theories. This is like K values. This like this C values curve enumeration theories. You also have A values curve enumeration theories, which are elements of in tensor A. Right. And then the claim is that there's a universal Grothendieck group values curve theory. So there's a universal element of this, which would be like a Grothendieck group valued curve enumeration theory. By definition, this is sorry. This what's the definition to be? A Grothendieck group about yeah. And this is the dual of
Because you are there.
right. So there you go. It is some so great like that. So yeah, that's my understanding for what he calls the Grothendieck group. It just topologically has a curve enumeration theory, which is the identity map from enumeration theories to itself, considered as an element of enum tensor enum dual, which is not quite grammatical, it's not dimensional vector space, whatever. Yeah, you just. Okay. Okay, so some evidence. So I was claiming that this is, the thing that the pardon meant to write. So some evidence is that this should contain some Gromov within. And some PT element. I actually have no idea what PT theory is. And I decided not to.
special case on this. What I'm worried about is special case.
So, what's in theory is going to be, what do I call it? So it's going to be some element frac m in yeah, in C relevance. Maybe something like this. It's going to be some Q U valued curve enumeration theory. Okay, so does this happen? So okay. So what do we have to do? We have to produce elements in each of these things, and they have to glue in some appropriate way with respect to pullbacks. Okay, so that now there's some stack bits. It enables stable curves in the fibers of X. Nothing to delta in. Now some not like this, where I take the image per cycle. This is not actually proper. So the image curve is constrained to be something, but so then it's proper if I restrict the genus or something. Right? Otherwise, you'll have some. But once I restrict to some, I think to some chi or whatever, it is proper. And this is the reason that we have this section. We have to keep track of this chi when we push forward. And now we're going to say, yeah, okay. And now if it's T I whatever, T I, it's proper actually. I'll write this. This is not disgusting, so you have to. This is pretty good. I definitely think it's not fixing a K-like structure. Yeah, definitely not fixing it.
I mean, it's really very impressive.
I think what kind of need, like the definition of the moduli space requires.
Yeah, I mean,
Symplectic structure, right?
that's right. So
The notion of J holomorphic.
yeah. So I guess this kind of a notion of a complex threefold, when you are dealing with coordinate theory, then it's not all that like what we're saying. It's not always it's going to be projected.
No, so yeah. Oh wait, so isn't a complex vector space automatically like canonically symplectic? Does it get a canonical symplectic structure from this complex structure?
So it's I'm not sure that, I mean, if you have a complex structure, then you definitely has so if you have a Kähler structure, then you definitely have a straight structure.
Yeah, that's what I'm.
Because you definitely have the two form, right? So once you have a complex structure, you definitely have two form, which is because in the separate case you want to define
Y where by Y, yeah.
but then you have to so to be symplectic, you have to get the form to be closed.
That's the problem. Okay.
That's the problem, and so that's kind of a more or less equivalent. If memory serve, this kind of simple calculation students do is to check the definition actually is the same. You know, once you under this condition,
Yeah.
the closeness is the same as scalar, or at least some kind of implication. At least, you know, there is some kind of, if it's scalar, then it doesn't feel like that.
Yeah, Taylor is very strong in the
Yeah.
Yeah.
And then, you know, there's some kind of open condition, like, you know, almost scalar or, you know, almost, because in this case, maybe it's almost scalar is enough.
Okay.
Almost complex is enough. Because almost scalar still has a closeness, but it is no longer kind of complex.
Okay. Maybe I should do this exercise. That sounds funny.
You see what I mean? So
Yeah, no, I see.
in this case, you don't even need kind of a complex. You basically only need almost complex. It's like it's J squared equal to minus identity
Okay.
in your space.
Yeah.
Maybe, I don't know.
Yes. Yeah,
But anyway, so I think you need some.
It's not, I mean, it's not, so, but you know what this is saying is, so what I'm saying is it may not be kind of all complex, threefolds are grown in theory.
Yeah.
But whatever so this is kind of a piece together, you're supposed to kind of get, whenever there is complex threefold, which can happen to be somehow the almost scalar or something, or like, you know, scalar, and then you can define this. It doesn't say it's kind of supported on everything, right? So this cycle N, it's just like it's
So maybe what you're saying.
yeah, it's
Because it comes from some limit over the whole,
yeah, and some
Category.
just
then maybe.
trivial. Yeah.
Maybe so. That can be true.
no, it can be true that if you pull back it from
No, there's no obvious pullback or anything, but let's see. So if you have a complex threefold, which then what you do is to define, you know, because if in PT theory you do require it to be, you know, complex, even projective.
You're right, be protected.
Yeah, exactly. So you certainly cannot define all the complex threefold, right? So
he actually in a talk does claim that he can or that he thinks it's fine or something.
yeah, but you know that because anyway, so at least Parham didn't plan that he's going to generalize PT theory and then, you know, use it. So basically, all we need to say is there's maybe some of this family has contributed to this cycle, and some family doesn't really contribute to this cycle.
Yeah.
Contribute nothing to this.
Yeah. I mean,
it's not supported on that kind of a family.
yeah. I mean, yeah. So, well, I mean, to make this confusing.
So
I'm not comfortable with the idea that M is like contributes trivially whenever it's just not defined like that. That doesn't seem like it can possibly work.
no, I'm saying because we're defining some cycle, right?
Yeah.
Whatever the cycle could be, you know, for real more or whatever. So, and this is the relative infinity. And so this kind of cycle, and then you have a space, and then you're trying to define a cycle. So it would be just on some components, you have some cycle, but on other components, you don't have cycle. The cycle is not supported.
No, I need to give you something everywhere. This is a limit.
Yeah, it's like trivial. And on that family is trivial. So particular x, which is not scalar over delta n, and I just declare that is giving you trivial, that's giving you zero. That's kind of final object, right?
Right. So then the problem is what happens when the thing is I have this and then this and and there's a compatibility imposed. Right, and it could be the case that, one of these things, it's defined on, it doesn't give you zero, and the other thing's
No,
not.
no, that won't change. It's kind of fiber, right? So this won't change your fiber. So if it's not, you have to act so to get to sort of a non-projecting to projecting.
Sorry, you have to
You have to play. So this doesn't change the fiber.
No, yeah, for both it's relative here. Yeah.
And especially when you do in the cycle theory, it's kind of a, it's sort of, I just imagine for some.
Okay, then that's completely fine. We could just take the category to be whatever things it's defined by. And yeah, the discussion will go through the same. So long as you have this. But yeah. I forgot. This relative. Yeah, okay, so. Yeah, so now we take relative. Virtual fundamental class and weight it by and I guess sum over chi or something. Okay, so then the Q is because of the W number, then the chi is this one proper or whatever. And then the click is that these attach to an element of this limit. And this follows from some sort of naturality of virtual fundamental classes that I think this is fine now. But, right, so I mean, my understanding is the point of this is like, there's a section in the paper where it talks about practical origin of curve enumeration theories. And they all seem to come from something like this that covers this, but has the better property that it does have a virtual fundamental system. Whereas this like a wild object wasn't even defined relatively to reduce things. So you can't go through. So what you in practice do is look for something that maps to it properly or locally properly, or something that does admit a virtual fundamental system. And the PT story is the same. And there's another integer parameter that you have to introduce, which is like the length of the co-kernel f over O, this the section defining PT. Okay. So given that this is an element of this limit, and this limit is grammatical, I think I want to continue working with this as the object that we call C relevant.
Before we kind of, whenever you feel like to close,
Yeah.
so maybe we should discuss, even though there are two absents, which they are going to be here next
I'm
week.
sure they're listening. I'm sure they're not.
So, what should we meet next week? Because next week, Wednesday, we have a tutor, right? So seminar, and should we meet on Friday? This Friday or next? Well, this Friday is kind of I don't know. I mean, if we were going to meet this Friday,
I'm going to finish in 15 minutes.
Okay.
Yeah.
So you don't need.
No, I just, no.
15 minutes or 15?
You don't insist.
1-5.
I don't insist on going Friday.
I don't insist.
So, I think
So then,
okay, so maybe I should say this. So, okay, so here it is. Yeah, so, this kind of for planning purpose. So we have. So today, what day is today? Sorry. This? Yeah. So it's Wednesday. And then it's Monday. So this is the 8th. And then there is that 14, and then after that we have 2 days, which is Monday, and then we have maybe like a 3-day basically blackout. So this is like 18, 19, and 20.
so this has a random
Yeah, Brad is like 19 and 20.
And workshop, and then
Adil has like the 18s and like most of the 19s.
Yeah.
Something like that, and or early, even earlier. Yeah, so these three days, they kind of more or less kind of like that. And then, so the only time for meet is this. And this is a possibility. And that day I'm not available, and then after that I'll be out for a week. And then we can do the online meeting if we want, or like similar time.
Yeah.
So there is, and then, with bear for me, maybe for try to be vigilant, try to kind of force myself not to sleep. Anyway, so then after that, we can come back to in April, but April then I feel is away, so we have.
Yeah, I mean, I got busy with Mark happy with his business.
Yeah, but I'm only still only at the end of the first week, so.
Yeah.
So, but it's for the. So then we have, maybe 31st. The 31st. Third. So second. I feel it's done for this week. So, but we can still, I don't know, I would think, can we?
Yeah.
All right, so, since you're not finished today,
Fortunately,
well, today, so we need someone to talk about 4 things. I'm not forcing anyone, but 4 things.
is there
Or anything you want to?
is that like we need a speaker? And what's there the topic of discussion?
Yeah, I think it's better to have a speaker, and the speaker, it doesn't necessarily have to understand everything, but maybe you already set a bad example, understand too much. So we will be all scared that we can't understand as much, but someone to kind of go through the material carefully, try to propose questions and maybe even answers, like potential answers, please not propose and propose potential solutions. And and then we can all discuss about those. And so what do you think should be the next topic after your talk?
Yes, the equivariant, just the encoding of equivariant stuff. I think it's pretty sensible.
So where is it?
I think section 4 or something. Section. It should be quick, really.
Should we all skip the the easy form part of the rest of section 3, like Algebraic structure?
I was just going to quickly talk about that before the end.
15 minutes? Oh, all right. So
yeah. Yeah. I'll quickly.
Maybe we'll let you talk first. Yeah. So.
Yeah. So I'm going to try to explain It's the algebraic structure on this. There's a couple of things I'm a bit confused by. Yeah, so what's the one that bothers me most? Yeah, the code unit from C star, it's, okay, so structure, okay. So the first thing is very easy. This, and we plot sum, because that's obviously what you want to plot, which is just the sum of sums. So 0, 1, 0 plus C1, well, this means exactly what it means. And there's a lemma. I guess it's not, but I think it's reasonable. The plus is proper. Right, and then just for that, remember the coefficients. N greater than to 1. So it would be reasonable that this is proper. So just this take the decombination to the same cycle into 2 cycles. So that's fine. There's an like this. So remember that each of these is a bounding over B, and if we take the fiber point over B, this is well defined. It's just saying the sum of 2 cycles lies in a given fiber if and only if each cycle lives in a given fiber. Also proper. And okay. So because we're using stick over B here. So there's an addition on around words because, well, like I said, I didn't actually have to stick over B here. Yeah, since this is proper, this is what we're so yes. I'm terminating with respect to proper words. And then some claim I'm wanting to prove is that there's not patches to all patches into an algebra structure. Zero complexity, which simply means some kind of built-in detectable back something. This is so not proper. Yeah, everything's this is kind of yeah. One thing I'm confused by is that so this algebra structure here is apparently unitable. I cannot spot a unit. I don't believe. Like he's at some point writes this such a thing as a commutative and co-commutative. That's fine. Unital and co-unital.
Unit isn't that just like you know the 0 cycle?
The zero is so 0 is not a cycle for one thing. So this, I mean,
0 is a cycle. Come on, so we should think about
you should add 0 in, you think?
Yeah.
Okay. And then for each thing. Okay, fine. I'm happy to just add 0.
it's that you know.
You can take a cycle on the empty threefold.
That just no. I'm going to do that. I'm going to do that, and that will give you the unit here, equivalently the full unit.
Yeah.
Of this. So
But here, you know, usually, you know, you think about cycles, but you know, you only have 1 0. So
Yeah.
you're not going to have a 0 0 gamma 1 plus 0 gamma 2 plus 0 gamma 3. So that doesn't change the properness.
okay, yeah, just adds 2 more fibers.
And we're not doing that.
Like
Like, you know, basically you have this kind of monoid and you have the 0 there.
Okay, fine, we just, I'm happy to add.
So because that usually in monoid, we do have some kind of zero, right? So I don't know about your definition monoid, but my definition.
So it's all monoid, yeah, sure, I mean.
So,
We can add zero,
and this might not be finite chain, but anyway, I just have a zero.
Yeah.
Zero.
I think another, there's another point of discussion on this one. Just a full product and then stuff. So there's some discussion about disjoint of cycles and whatever, and I can't parse it. I have no idea what it's supposed to mean. So Hardy constructs some full multiplication on. So this is the more important. This is more. Yeah, exactly. Yeah.
So the swing unit must be on, like not on itself, right? So how do you do?
Yeah. So I don't want to try to make sense.
Oh, okay.
Does I just want to show you like
We're going to define the
I'm going to define a co-product and argue that it has to be the same as the one he defines. Okay, so if log is some central space, then this is proper. And this is diagonal and physical. Well, why is the co-algebra in this case? Right, so this is all the co-products. When we're on so it's proper. It's not unital. This is not unital. Right, so they're distinct from like supported homology is unital if and only if one is compactly supported, if only if the case is compact. So this is unital just that we're all the same as follow.
One more is like homology or co-homology?
Homology, yeah. Sorry. When the PM goes up, it's sort of implicitly goes up at all time. Right, and this is completely natural and like quantitative and it can use absolutely everything. In particular, there's some actually multiplier. There's something on this. Yeah, and this is unital. Co-unital. So co-unital, I need to reduce something out of it. And now we think.
But sorry, you're saying this one, I'm a little bit lost. So you were saying so this you use a BM to define the whole product and that give you the product?
Sorry. Sorry. I keep changing between BM and REL infinity. So this is.
So that define the co-product, right?
Yeah, this is the co-product.
And what do you mean? Okay, and what do you mean by you were trying to define the
co-unit?
So I want to values.
No, but actually we only define the product. Is that?
Yeah. So this was a product before from the sum of cycles over there, and just the diagonal map. I mean, there's basically always a co-product on Borel homology. Coming from the diagonal map, so long as this is, like if it's space, like not a stack or whatever, then there's always something. It's completely natural. So it passes to the limit. So we get something in here, which is a co-product on this. And now I want to specify a co-unit, which means it maps to C, and it's like evaluate on the empty fan. So I checked, and his co-unit also involves the empty set. So I'm certain this is correct. But that makes sense of what he said. But now I argue that it has to be the same as this, so we can forget about this disjoint linear cycles thing. And the reason it has to be the same as this is because since this is completely natural, because it's the diagonal map, it commutes with every other product. This is co-unital, his is co-unital, apparently. And then it actually builds an argument because we did the same co-product. So this is such a stupid way to get around the fact that it makes sense of this co-product. So I can help it on because you can use a lot of algebras. Each is a multiplication with respect to the other, then they agree. And there's a co-version, so long as they're co-used. So in other words, the co-multiplication on C rel infinity has to be the one coming from the diagonals touching together. And this is more important than the multiplication on C rel infinity, because this is dual this co-multiplication is dual to the multiplication in the group. And the main theorem is a theorem about the multiplication. So this is more important than the direct sum of sums.
So these are all in your notes?
Yes.
Great, thank you.
And yeah, and something I didn't write, but would like to understand is that, like, so the end goal is that this is like free. Well, it's not even, but it's generated by something that is free. And like when you have an commutative and commutative bialgebra, and it's unital and coordinal as well, then in general you kind of expect it to be basically free, or like at least the universal enveloping algebra of the algebra, like the Miller-Moore theorem that tells you this is true.
Sorry, why do you, if you have bialgebra, why do you have these figures?
So the graded bialgebra and co-commutative. And then if it's finite in each dimension, it's the universal enveloping algebra of the Lie algebra of primitives. So
you can't. So I mean, can you have something which is kind of a very artificial, but it's kind of have many like infinite generators on each degree or something?
Yeah. You could just. I mean, polynomial algebras. But like what I meant is really whenever I see a bialgebra or it's just co-commutative and coordinal, you look for elements that satisfy this. So for example, X in the Lie algebra, the universal algebra satisfy this. These elements here are called primitives. They form a Lie algebra, and a good approximation, I guess, rather, that you can make is that the algebra should look a lot like the universal enveloping algebra of the universal enveloping algebra of the Lie algebra of primitives. And then if it's actually finite dimensional each fixed grading, then this is a theorem. This is the Milner-Moore theorem. So this is obviously not going to be finite dimensional grading, but like I want to actually look at the Milner-Moore theorem, so to know if there's like some chance that you could hopefully identify the primitives here. And like geometrically, and then.
Really? So you're saying that this theorem of Is has nothing to do with revolve?
No. It has to have a huge amount to do with all of those things. It has to have a huge amount. So my hope would be like, okay, right. So firstly, there's no way that the Milner-Moore theorem just spits out a theorem like this, right? Because there's no way he accidentally proved it only for some very special case when it's true in complete stupid generality. Right, so then the only thing I can imagine would be that under suitable cases, you can choose some nice bigrading that makes it finite with respect to some bigrading under restricted conditions. And then Milner-Moore applies. Right, because Milner-Moore has a finiteness assumption in it.
So maybe you're saying that if you impose whatever conditions, this transversality might be equivalent to the fact that it would take, I mean, he's taking some truncation anyway, right?
Yeah,
This is some virtual dimension, at most zero.
Yeah, that's where I'm hoping something like this imposes some sort of.
Right.
Exactly. Yeah.
Condition, but yeah, I mean.
Well, you still need to do a lot. You also need to identify the primitives, which is a geometric question.
Yeah.
Right, and he's claiming that the primitives are like something generated by a covariant class.
Yeah.
It's just like, as a general rule, like some enormous objects, you try to compute its cohomology. The only other example I can think of is like in the stuff that Arcadia does, away from the Joyce vertex and so on, when you compute the cohomology of some same thing like the stack of vertexes, that's what we predict the horizon. It's always just trying to argue with Milner-Moore. It's just not, you can't get your hands on one at all. Right? So you just hope that it's free and then try to argue with Milner-Moore.
Okay. That,
Yeah, sorry, yeah, that is it. Yeah, yeah.
okay. So, yeah, I guess, I don't know, I mean, maybe because 14 and 17, Yuki, do you want to talk about it on 14th? Or you don't have time to do it, or, because we, so the 14th is gonna be some, if I don't misunderstand what Emile was saying, it's basically the sort of a chapter, section 4, right?
Yeah, 4 point.
And it's kind of a, he's talking about, so first of all, kind of simple equivalent quantity that everybody understand. Then he's trying to kind of do some, he's going to try to do something about equivalent quantity. I think it's like 4.3. I think that's probably the
Yeah.
is. He's going to choose some cycle, because equivalent quantity is something over BT. And then he's trying to kind of choose. So usually our equivalent classes are kind of it's you want to think about that as kind of a class which is kind of subject to BT. But here he actually choose some cycle inside BT, like this kind of a CP infinity. Choose some or actually co-cycle inside the BT cell, so that it like in the total space the same homage. If you want to get some homage to homage, that's how I get from kind of his talk. I don't know. I mean, I forgot most of the detail, but you can, because you have like this kind of a vibration over BT. Let's just think about CPN, something like that, because you can always talk about CPN, and in any homage theory, you're dealing with it's like, when n is large enough, that's enough.
Yeah, it's stabilized.
And so, but if you want to take some cycle, some specific kind of a class there, you might be able to kind of trade the base dimension with the fiber dimension, etc. So that's sort of my impression, but I don't quite remember all the details. And it should be accessible to you, but I don't know if you have time to talk about. I think the meat is 4.3, and you have like 9 days. Not sure. There's something there. Share the two. Yes. So, no, let's try to work on that, and I will see what I can do. Nobody can do, and I'll try to. There's something in this which sort of help with the argument he's going to do later on. I forgot what's something.
And then maybe, yeah.
Yeah, okay, maybe I'll so tentatively like self-assign to me, and then we'll see how it works.
Okay.
Yeah, so you covered basically everything up to section 3, right?
Yeah, it's the next section, I think, is immediately Algebraic.
See what I can do. Last week and this week is one book. Hopefully, there is always, hope that next week is better. Good enough. Yeah, this Friday, it's Okay. Let's.
Actually, if someone has to turn this, it's very unsettling.
Maybe if you go get Andrea, so she.
Yeah, it's our before.
Area was already. So.
Sometime not today, it's the entire, but. Don't have anything. Immediate there. Alright. Okay. Tomorrow, there's here, right?
Yeah.
So after tea. Tea and.
Yeah. Before, yeah, in some swings. Anyway, can I ask you though? I was trying, so someone asked me and then I realized I didn't understand that properly, so so that, I think you were saying that the line marking. So if you have line marking of, you can think about it as map in BC over C star, and which this map is equivalent to a section of the line boundary. And this map actually degree 1. Is that it?
One,
So this one,
yeah, but then you have to put some stability conditions, so. The linearize here by character, which is sort of.
yeah. And it will feel free to run in the right. Okay,
It's still on balance, one, so. Okay. So,
and then,
right, then you. Right, so the length then sort of depends on.